Okay, I think we can start. Welcome back, everyone, to the next session. For this session, we are going to start with Nic Brummell from UC Santa Cruz. He's going to talk on looking forward in connections, progress and problems. Nic,
Okay, hello everybody. I was tasked loosely with waking everybody up after lunch and doing a very sort of similar thing to what Lauren did earlier this morning, but again to remind you this afternoon and to maybe with a little bit more of a forward perspective. So that's my plan here, looking forward in connections, progress, and problems. Just to remind you, once again, bears repeating that surface flux emergence, sunspots and active regions in particular are our main window into the solar dynamo. That's pretty much all we have, really, because we can't see much deeper into things very much, apart from some internal rotation with heliosmology and things like that, of course. But, that in itself gives us lots of very interesting information because a remarkable degree of order emerges out of the chaos, Hale's polarity law, Joy's law, the solar hemispheric helicity rules, etc. And these are very strong constraints. And these can be our clues, our major clues as to how to try and understand things. A big part of that is that, sunspots, active regions have become recognized as these bipolar magnetic regions, which are essentially, all we know is there's some sort of smaller elements torn off the solar dynamo larger scale field. And so we have this little mental picture of, just because it emerges as a bipolar region, that it's a little piece pointing through thing. And this concept of flux tubes came up, but it's a very, very imprecise concept. But that is the basis of our full intuition on how a lot of stuff works. So let's talk about that a little bit. So I want to talk about things we have done and things we have not done. And once again, as Lauren said earlier, this is a very personal and we'll probably miss a lot of important information, but in only 10 minutes, I don't have time to cover everything. So apologies if anyone gets offended. But things we have done and not done, let's start with things we have done. We have built some intuitive theoretical understanding of how a dynamo process can produce large-scale dynamo fields. So in general, this is mean field dynamo theory. We've also built some nonlinear dynamo simulations that actually exhibit dynamo cycles in the large scale field. And some of these are direct numerical simulations. Some of these are ILES simulations, etc. So there's various flavors of these, but we have not fully nonlinear, self-consistent dynamo simulations that cycle. We've also examined the breakup of large scale field into smaller scale components via instabilities. There's lots of work on this. But in general, this is done through imposing some sort of large scale field in a non-self-consistent manner in the first place. That's something we've done lots of. And from there, we've examined the vertical transport of magnetic flux independently of the creation process, so ignoring the creation process. And there's lots of elements to this as well. There's large-scale downward transport, magnetic pumping of large-scale magnetic field by convection. There's small-scale upwards transport via magnetic buoyancy or a variety of other instabilities and the rise of flux tubes. We've done lots of playing with this, lots of games with this. Some of these are quiescent, rising through quiescent backgrounds, some of them rising through convecting backgrounds. We've played with quite a lot of this stuff, and I'll talk more about that in a second. And the other thing we've done is examine the detailed emergence of pre-existing magnetic flux structures through the very near photosphere. So stuff very close to the surface, some of which you saw today. That's been getting deeper and deeper, so that's improving. But once again, pre-existing magnetic flux structures, and in general, close to the surface is the way it is. So those are things we have done. What are the things we've not done? Well, some of this is for another day, but we haven't understood well the connection between the theoretical ideas, in other words, mean field electrodynamics, and the nonlinear numerical simulations. It's not clear that these two things are the same thing at all. So maybe that's for another day. But maybe more importantly for today, we haven't produced any sort of fully nonlinear simulation that is both a cyclic dynamo and which spontaneously creates smaller cycling sunspot-like bipolar magnetic regions, active regions type things, structures that are emerging spontaneously and naturally. So that's something we have not yet achieved. So this has also implications for dynamos. What does this say about Babcock-Layton type dynamos? Because there are no sunspots to break down in this scenario, and yet we still get a cycling dynamo. What does it say about things like alpha suppression? Let's ignore that. But maybe the biggest question here is then becomes, are bimodal magnetic regions, are they necessary or just a symptom? So how involved are they in the dynamo cycle? So that's a very important question. And we have not actually yet determined where, so therefore, from that problem, we have not determined exactly where sunspots and active regions originate from. So with those old ideas of tachoclines, it could be the convection zone, could even be near the surface. At this point in time, we have no idea. And we haven't produced any model in terms of smaller scale structures like active regions, BMRs, that spans the origination process to the emergence of the surface. We have not been able to do that at this point in time. We have some deeper and deeper models now, but none of them that include the origination process. So, we have this background intuition. I call it Heath Robinson and Gold Ruberg machines. These are these weird cartoonists that from the past. Heath Robinson is a British one, Rube Goldberg is an American one. But we produce these cartoons of how everything works. And we have this, this is an old cartoon I drew thousands of years ago, which just sort of embodies this idea that, some sort of field is produced by dynamo action in the convection zone. It gets moved to the tachocline, transported to the tachocline, where it gets amplified by the shear there. And then there's some sort of instability, and then that instability creates fluxus, which rises through the convection zone. Maybe there's some recycling as we go through. Sorry, does somebody have a question? No, okay, carrying on. So this is the standard science scenario. The tachocline is a great source of shear. So, that came up. Mean field electrodynamics relies very strongly on that as the amplification mechanism. So the tachocline is a natural choice for that. It's also a good place, if you want to just keep pumping stuff down there until it is strong enough to emerge, it's a great place to store. So it's a very natural place, and that's why we have this sort of standard view of this thing. And then we assume there's some sort of large scale field instability that creates so-called flux tubes. I mean, if they're probably not isolated flux tubes, but there's some instability that creates sort of smaller scale or smaller wavelength field. And then these structures rise through the convection to the surface and emerge. But like I said, tachocline, is this the right location? We don't know absolutely for sure. And in terms of instabilities, we've done lots and lots of great work on instabilities. I'll mention some of it in a second. But we have not coupled the origination of the large scale field to these instabilities themselves. The field is usually just placed as an act of God in your simulation, and then you look at the instability of that field. Now, it may be consistent with things you assume are down there, but there is no coupling between those two processes. So we still have disjoint instability in flux tubes and dynamo simulations. There's nothing that joins the two. And the big thing, we say structures rise through convection. How the heck do they survive? The more and more I work in this subject, the more and more I realize I don't understand how that works. Anyway, moving quickly because I don't have much time. Alternative locations of origin of flux tubes. A lot of people now have purely convective dynamo simulations, which they would claim have something which looks like bimodal regions, bipolar magnetic regions, BMRs. And generally, these are little pieces of flux. This dynamo creates things in toroidal bands, wreaths, some various things they've been called in the past. And these little pieces of flux emerge, and there's many simulations, maybe originating first with Nick Nelson, but there's lots of people, Yu-Hong Fan and Gustavo Aram, and lots of people have done these sort of things. But little pieces of flux that emerge, and are these things related to BMR as active regions, sunspots? It's hard to say that they are, because obviously these emerge through convection, and so they're much more random and much less ordered. So how do you get these things not dictated by the convective flows, but dictated by some other more ordered process? This is a difficulty with this thing. Maybe this is where the tachocline comes in. Most of these simulations do not have tachoclines. I'll come back to that.
I think you have about a minute left.
Okay. Alternative locations of origin at the surface. I'll come back to that one in a second. Production of structures, we're a little better at this. Much of our perceived understanding comes from thin flux tube theory, right? So there's people who cite the strength of flux tubes at the base of the convection zone, rise time, Joy's law. A lot of this is thin flux tube theory, which we know not to be correct. These do not have internal dynamics. Twist is important, and these tubes are not really isolated in reality. So this is not correct. So we need to move beyond that understanding. So we need to reevaluate a lot of those things which we think we know for sure, but only on the basis of thin flux tubes theory. We've got better. There's been many simulations of the basic instabilities, but in general, there's no convection or no origination process. There's this one nice one that Jeff Fassel and I did a while ago, which involves the origination process, but this one had no convection. There are things where there's no origination process, but convection, and you saw a great example of that today with Toriumi-san's talk today, which was fantastic, a little bit fancier than this one of mine that I did with a graduate student a while ago. But we played these games quite a bit. And then there's the opposite one, large-scale field gets pumped. So the big questions, lessons learned are, tubes must be surprisingly strong to survive convection. The magnetic energy in a tube has to be at least some smallish order 1 to 10 factor larger than the maximum kinetic energy in a convection. Then that becomes a bit of a problem because the Reynolds number of convection in the solar convection zone is so high, so it's very, very energetic. In those ones we did with shear, including the origination process, you had to make the shear surprisingly strong to make these things magnetic buoyantly enough to rise. So that's a problem too. And then there's this complex interaction between the downward transport, pumping of large scale fields, and upward transport of smaller scale things. So how does that work? Is it how small a scale? What is the relative scales you need between magnetic field structures and the size of convection for it to be able to rise and not to be pumped? And then how do we take into account the three-dimensionality of those things and their wakes, and how does that interact with convection? This is something we haven't really done. So there's real issues here, which I'll go into in the final slide. So, and the other thing was these amazing simulations that happened at the surface, but Lawrence sort of talked about this. There's a lot of, these depend, you sort of get in what you put out, right? You put in a flux tube and it emerges at the top. Where did that flux tube come from? Deeper down, not deeper down, we don't know, right? So that's the problem with these simulations. They're fantastic, they're beautiful, they produce very nice things which match observations, but you're basically putting in initial conditions in these things which are very, very ad hoc. So, and then one other thing I mentioned here is some people now believe that everything happens at the surface, and this is a kind of an interesting thing that could be pursued. I'm going to skip over that. So I'm going to just go to my last slide. So we now have dynamo models that actually spontaneously create tachyclines. Lauren didn't make too much of his own work this morning, but that's one thing that's happening now. Are we going to get with these to the point where we see spontaneous instabilities in a tachycline? I think probably not. Yeah, it's going to be hard because they're not realistically thin enough or anything like that because we're not at solar parameters, but that's an interesting avenue. If we believe in the deep origin, we need to combine the origination of structures from dynamo, toroidal field, and transit towards the surface. Everybody knows this. Everyone talks about it. Everyone knows it's extremely hard. The more I think about the deep one, like I said, the harder it gets because the convection is extremely strong. How strong does a magnetic flux element have to be to survive that convection? How do you get it to be rotationally influenced? If you make convection higher and higher Reynolds numbers, the scales get smaller and smaller. The turbulent scales will get less and less rotationally influenced. People want those rotational scales to influence the magnetic flux tube, but that gets more difficult to understand how that can happen. So that's the other thing. And then, last sort of controversial thing, could you circumvent all these problems by having everything operate at the surface? That could be kind of amusing. Nobody knows quite how that could work yet, but that's a future possible thing. Anyway, there you go. Just try to stir up a few thoughts in your heads. I'll leave it at that.
Thank you, Nick. Thanks for an interesting talk. We do have one question in the chat by Shashant. Lauren has answered it to some extent if you want to add something. But yeah, any other questions? I see Lauren. Lauren, go ahead with your question.
Yeah, thanks, Nick. Something I just thought about as you were speaking was we're always talking about how these things can't really survive transfer across the convection zone. I guess, do you think, is it possible that, there are flux tubes in the tachycline and then they do get completely shredded and then in the near surface shear layer, they sort of get collected again? I mean, is that a possibility or no?
I think we don't know. I think, yes, it's definitely a possibility, but there's nothing that has demonstrated that yet. I think that the thing to realize is, and I realized this from the magnetic pumping calculations, is magnetic pumping is it's like a mean field effect. It's something that acts, turbulence acts on a large scale field, and on an average, it moves a large scale field down. On the other hand, if you look at those simulations, there's always stuff going up and there's always stuff going down. It's not like it's a static process. On average, things move down. That's why mean field theory works for that sort of stuff. But there's always like elements of magnetic field rising through buoyancy, and there's also always stuff getting sort of torn down by the convective downflows. So stuff does get to this, in that fairly stratified convection, stuff does reach the top. And it's just a matter of, can you make that the thing that you want to reach the top? Or is it just a random piece of stuff? That's what some of the bigger convection simulations are finding. Or can you make that something more ordered and something, the piece that you want to reach the top actually reaches the top? So I don't know. But to answer your question, I think it is possible there's reconstruction of the surface.
Thanks, Nick. I think we can move on to the next talk now, and we can take some questions in the chat. So for next talk, we have Petri from Institute for Solar Physics, and he's going to talk on simulations of entropy driven convection. Yep.
Thank you. Can you see my screen?
Yeah.
Can you hear?
Yeah.
Okay, good. So many thanks for this opportunity to present this this topic. So you see the topic, and okay, I'm technically still at the Institute for Solar Physics, but I will be moving to the University of Graz in Austria next year. More about this later. And I apologize that this talk has a little bit of a marketing flavor. So I give you the conclusions already here. So I'm talking a lot about the new paradigm of convection. And this was a sales pitch, and you will see the result of the sales pitch on the last slide. But the new paradigm that I'm talking about here is that deep convection in the sun and in stars could be affected very heavily by the surface. That convection, deep convection, is driven by surface cooling, and it's highly non-local and leads to a strong entropy rain and largely sub-adiabatic convection zone. And this has then implications for the convective conundrum. I will say a few words about that shortly. And there is a paper about this proof of concept study, which you can read if you like. So if we look at global dynamo simulations of the sun, so here we see the solar magnetic field, which already has been shown a couple of times in this meeting. There are some simulations here. I only show my own simulations, but there are also several others that obtain similar magnetic activity as in the sun. Usually this kind of cyclic dynamo solutions are obtained for somewhat more fast rotation than in the sun, typically around 3 times solar rotation rate. And to me, this is one manifestation of the convective conundrum. So now we come to the real marketing part. So some things here are simplified for a non-specialist audience. But the convective conundrum is essentially the failure of global simulations to reproduce first-order observables in the sun. So I'm a Fortran guy, so first means really first. So these are really major things that we don't capture with global simulations. One example is the global magnetic field of the sun. The second thing is the differential rotation. So here on the left, we see the helioseismic result of the solar interior rotation in the convection zone, and slightly below, if we take a simulation where we take the solar rotation rate and solar luminosity, which are the key parameters in this problem, we often get something which is opposite. We get a fast pole and slow equator. And if we get this major problem, then if we look at the induction equation, if we have only one term there that can generate magnetic fields. And if we get the velocity incorrect, there is no hope that we will ever get the magnetic field correct either. So this is the convective conundrum, that we don't reproduce the flows in the sun the way that they are actually. Another way of looking at this, and this is again a simplification of the actual data. So there is a paper by Aaron Birch where he collects different observational and helioseismic inferences of convective amplitude in the sun. So this is a power spectrum of the horizontal flows. And most of the observations here indicate that there is very low power at very large horizontal length scales, as opposed to global simulations where these large-scale flows are actually the dominant contribution. And these are the giant cells or banana cells or thermal Rossby waves that we observe routinely in simulations, but which have not been observed from the sun. I should also here mention a recent paper with further helioseismic results, which are more in line with this, what seemed to be an outlier, the Creer et al. Result, but this new study is more in line with that result. Nevertheless, there is a discrepancy between what we can see in the sun and what we see in simulations. So these giant cells or thermal Rossby waves are apparently missing from the sun. Right. So there's clearly something rotten what we do with convection simulations. So the textbook wisdom of stellar convection relies largely on mixing link theory. And there the convection is driven by an unstable temperature gradient locally, and typically rotation and magnetic fields are ignored. And this has really had a profound effect profound impact how 3D simulation setups are constructed. So they are constructed such that there is a convectively unstable convection zone, and this is enforced typically by a fixed profile of thermal conductivity, for example. Whereas this new paradigm of deep convection relies on surface cooling and deeply penetrating flows from the surface. And this is a concept which was introduced by Henk Sprout already in the 1990s, and there is a adaptive mixing length model by Axel Brandenburg from 2016 that takes this effect into account. Magnetic fields I will not talk about here. I will mention them on the last slide again. So what this mixing length theory essentially captures, and what all the simulations also capture, that there is heat coming from below. And the radiative flux or the radiative fraction of energy transport is gradually reducing towards the surface. And this all the simulations can capture because this happens on length scales that we can resolve. However, surface cooling happens on a very, very thin surface layer. That's only a few tens of kilometers deep in the sun. And the solar convection zone is 200,000 meters deep. So this is a really, really, really small fraction. And this is something that we cannot self-consistently take into account in global simulations. And furthermore, the surface cooling is highly non-uniform. So often simulations, they either assume a constant flux or a constant temperature at the surface. And this is not exactly what the sun is doing. Okay, so this is now called the new paradigm of convection. It's not exactly new because this was already introduced about 30 years ago. However, it's of course new compared to the mixing length theory, which derives from the 1930s. And essentially the formalism, which is still used in many stellar evolution codes, is from Böhm-Vitense from 53. Okay, so let's look at the proof of concept things. So if we look at simulations with the, say, current paradigm, there's a uniform surface cooling, and this leads to giant cell convection. So these very large convection cells here, and poor separation of scales. So there are smaller convection cells near the surface, but they then merge into these very big ones at the base of the convection zone. However, already in these simulations, the Schwarzschild unstable part of the convection zone is only about 60%. So there is a substantial layer below the Schwarzschild unstable layer where things are convectively mixed, although we are not really doing anything very special here. However, if we go to the new paradigm where we have this non-uniform surface cooling, so here this is facilitated by artificially putting cooler spots here at the surface. So these are like cold fingers which are penetrating a little bit into the convection zone. And they lead to this highly non-local entropy rain. So there are these plumes which go all the way through the convection zone. And in these simulations, these are actually in scale, so the convection zone is actually much deeper in this case. Furthermore, the sub-adiabatic part of the convection zone is then even deeper. So here, more than 70% of the convection zone or convectively mixed region is formally Schwarzschild stable. These were made with the pencil code simulations. Okay, let's look at this non-locality a little bit further. So here are horizontally averaged energy fluxes from sort of the standard simulation. So we have what I here call a buoyancy zone, which is the zone which we would get from mixing length theory. So we have a super adiabatic stratification and a convective flux, which is going outward. Then in the middle here, there is at the bottom, there is the overshoot region where the convective energy flux change is sign. But in the middle, there is the Dierdorf zone where the convective flux is still outwards, but the stratification is formally Schwarzschild stable. And this is the one where we didn't have any of these cool patches at the surface. Then we go to an extreme case where we put 100 of these patches at the surface.
Petri,
And then what?
Sorry.
2 minutes. Yeah. Okay. So then the buoyancy zone is reduced. The Dierdorf zone is substantially increased, as is the overshoot zone. And much of the stratification here is weakly subadiabatic. So this is not really, it's not radiative because everything is transported by convection, or much of the energy is transported by convection, but it's still slightly subadiabatic. There's some support from solar observations or helioseismology that support a weakly subadiabatic convection zone in the sun, and also of flows on small scales related to supergranulation. Okay, so I will skip more or less this slide. So the convective scale actually is not very much changed, even if we introduce these cooling patches. So the horizontal velocities still peak at the larger scales, but there is a sensitivity to patch placement here. So if we get totally random positions, these are now static positions. So if we get random positions, there are these voids where we have no cooling spots, which are the red spots here. And then there are concentrations which actually then drive large-scale convective flows. And if this is optimized so that here just by eye, making sure that there's nothing really clumping together, or that there's no voids where there are no downflows, then this situation is a little bit better. Here is a comparison of 4 different runs, 2 with totally random placement, 1 with this semi-optimized case, and 1 where it's fully optimized. So this means that the cooling spots are equidistant. So there is a grid of 7 by 7 cooling spots here, and then we see that even the horizontal velocities are reduced at the scale of the domain. But this is highly artificial. So this is a clear development for this method. Of course, these are now static, these cooling spots, so they should be made dynamic, like in the study of Nelson et al. In 2018, and of course affected by the flow, mean flow, or the local flow. But this is then work in progress. And if I may, then I will use the last slide as an advertisement for essentially further development of this concept, and also of the magnetically influenced convection. So this was a sales pitch to the European Research Council for advanced grants, and this was granted. And the name of the project is New Paradigm of Stellar Convection, or NEOCON. That's why I was talking about the new paradigm all the time. This will start in about a year from now in the University of Graz in Austria, and the project will last 5 years. And the plan is to hire 3 postdocs and 2 PhD students. And 3 of these positions should be available starting 1st of September 2026. These are not yet announced, but they will be announced at some point. But if you are interested, or if you know somebody who might be interested, please contact me. Thank you. That's all I had to say.
Thank you, Petri. Do we have any questions? Yeah, Nic.
Yeah, thanks for a very, very interesting presentation. I just had a quick question. The cooling plumes that we might think of from the photosphere are, like the intergranular lanes, I would guess. And those have to traverse a region where the density varies really, really dramatically. So in these models that you showed, what's kind of the density contrast that you were able to to model in these? And do you have a sense of how that relates to the coherence or the decoherence of these plumes as they descend?
Do you mean the total density stratification I have, or between the plumes and the ambient?
I would say just the total. And do you have a sense of how the background density stratification impacts the coherence of the plumes?
Okay, so the total density stratification here within the convection zone is something like 30. So this is, of course, much less than in the solar convection zone, where it's 1 million. And okay, here they stay more or less the same size, these downflow plumes, but there's studies of individual plumes by Evan Anders and company, and they found that when you increase the density stratification of the atmosphere, you actually find that these plumes tend to decrease in size when they descend, the higher the density stratification you have. So in the sun, you would expect these to be very, very small, if they really are coming from the intergranular lanes. There's, of course, the possibility, and it's likely that there is some merging of these downflows near the surface, and then you might get somewhat bigger sizes, but these are likely to be quite small if they work the same way as in this proof of concept or in these earlier studies.
Thank you. And again, very interesting talk.
Thanks.
Sasha, Lucas, can you please put your questions in the chat, and maybe Petri can answer over there, and we can move on to the next talk?
Maybe you can ask, because Petri can disconnect. He's late for him, and he can.
Well, I'll be here until the end of this session.
Okay, I'll ask him discussions then. Yeah.
Sorry,
okay.
Sasha. Thanks. So for the next talk, thanks, Petri, for the very nice talk. So for the next talk, we have Kinfe from Southwest Research Institute, and he'll talk about the possible role of near-surface convection in maintaining the sun's latitudinally uniform photospheric emissivity. Kinfe, take it away.
Yeah. Do you see my screen? Thanks, Bishak.
Yeah.
Okay. Okay, thank you. And today I'm going to present the possible role of near-surface convection in maintaining the sun's latitudinally uniform photospheric emissivity. And saying this directly, I'm going to go to the introduction, which is the near-surface shear layer. This region is a strong radial shear in the upper convection zone of 30 megameter of the convection zone, and it is characterized by the strong radial gradient of the rotation and characterized by a strong convective turbulence. And observation shows that in the photosphere, its luminosity is remarkably uniform from observation. And as you can see here, this is from the 2005, and the radial gradient in the near surface shear layer is actually decreasing, and which in general the differential rotation shows that fast at the equator and slow at the pole. And the question is we are going to see here is that the near surface shear layer is fast equator at all. That means we will see in our simulation this, and we are going to see as well the what looks like the temperature distribution in the near surface shear layer. Does it nearly uniform? Will be the questions we are going to deal. And saying this, what looks like the differential rotation and thermal variation from the global simulation actually in a rotating convection. This is from these plots are from Kamisasa and Featherstone 2022, and that shows the upper panel shows that the differential rotation interacting with the convective flow speed. And in the left panel, which is in the upper panel in the left, we saw that the convective, which is fast equator, this is from the convective time. When the convective time scale is longer than the rotation period, it develops actually a fast equator relative to the slow pole, while when the convective time scale is fast, it develops a fast pole and relatively slow equator. And the photospheric is actually a very short time scale compared to the rotation period. And from this, we can say that the near surface shear layer convection can be developed as a weak rotation in the model is the important question to see. While when we see the thermal variation in terms of the convective flow speed, the slow convection actually develops a warm pole and warm pole relative to the slow, relative to the cool equator, while the rapid convection develops a cool pole relative to the warm equator. So from this we can see that the simulation predicts a strong latitudinal temperature difference. And now when we see the motivation and the background, while that leads to the questions are, from observation we saw that the deep convection is strong with a strong rotation, while the near surface is weak rotation, but still it develops, it retains a solar-like rotation. So we can ask that why the near surface shear layer actually a solar-like under a weak rotation, and it can also develop a thermal wind balance. Why I'm saying this is in the near surface shear layer, a paper by a study by Ja and Chaduri 2021 shows that the near surface shear layer maintains a thermal wind balance. And the other question, the third question we want to ask is that why simulations predict a strong latitudinal difference while observations show that a remarkably uniform luminosity or temperature at the surface. And we can mention here that the photosphere actually maintains a remarkably uniform luminosity by Can 1989, 98. And from this, these are the questions and motivations leads us to the simulation. So our numerical experiments, we did consecutive, or we construct a series of 3D fully nonlinear rotating convection model. We use to run those in a Rayleigh convection zone code, which is open by Nic Featherstone. And here we the key controlling mechanism is the convective Rossby number, which is the rotational time scale to the convective time scale, the ratio, or it qualifies the rotational time scale to the convective time scale. That means when we have a low convective Rossby number, it is slow convection, while higher Rossby number is rapid convection or slow rotation. So the lower boundary condition in our model is latitudinally varying flux, which is fixing to the entropy gradient in this way. Here, we also use A is the thermal forcing in the lower boundary, and this graph shows that the latitudinally varying flux, when we force when we increase the forcing A, it develops actually, it develops enhanced or warm poles, while the equator is depleted in somewhat. So that means the higher value of the thermal forcing leads to stronger flux concentration near the pole, while corresponding depletion near the equator, at the equator. So this leads us to the question actually, in the upper boundary, we use a uniform entropy variation that leads us to vary the corresponding heat flux at the upper surface. Then this leads us to the question. We know that we said the deep convection zone is warm pole and cool equator, while the near surface shear layer is warm equator and cool pole. So what will be the interaction of this at the surface? What will be the response of the near surface shear layer with rapid convection to the established latitudinally varying flux at the deep convection zone? What will be the differential rotation and the flux at the upper surface? What looks like the thermal wind balance in at a high convective Rossby number will be the questions that we can raise here. So,
Kinfe, you have
yes,
about you have
okay.
about remaining.
Okay. So this, we can see that the latitudinal variation of the differential rotation, as we increase the thermal forcing, it leads to weakening the differential rotation at the, actually, particularly at the higher poles, at the poles. And when we see its corresponding thermal wind balance in a high convective Rossby number, it leads to the thermal wind balance, as we can see here. The thermal forcing, actually, it maintains is more to the thermal wind balance in a high Rossby number. We know that in the low Rossby number, that the thermal wind balance is the hallmark of the low Rossby number. And we also saw that we can also see what looks like the force balancing in the geostrophic balances from the on the momentum equation. Actually, the dominating forces are the Coriolis force and the pressure gradient. So it is in geostrophic balance. It is in well geostrophic balance. So the other point we want to see is, as we increase the convective Rossby number, as we vary the convective Rossby number, it leads to the imbalance. It's not in thermal wind balance. It actually wipe out. So that means there is a threshold value in the high convective Rossby number that can be in thermal wind balance, and when we cross that threshold value, it leads to wipe out the thermal wind balance. The same is true for the geostrophic balance, actually. And we saw that the important point we need to mention here is what looks like the conductive flux at the upper surface between the two boundaries. What we input at the lower boundary is this. That means it prefers or it enhances the polar flux, while at the upper boundary it becomes uniform. Still, we can see that as we increase the convective Rossby number, it becomes more uniform flux. Its response is more uniform, the upper flux. So, but in lower convective Rossby number, relatively lower convective Rossby number, it retains the latitudinal input at the base of the convection zone. This leads us to the summary that the high convective Rossby number, it actually homogenizes the latitudinal flux, And the other important point to mention here is that at high convective Rossby number, it maintains a thermal wind balance and geostrophic balance, while there is a threshold value that violates the thermal wind balance and the geostrophic balance. Thank you, Bishop.
Thank you, Kinfe. Maybe we can take one quick question and then move on to the next talk. Does anyone have a question? Okay. If you have any questions, please put it in the chat. Going forward, next talk is by Nic Featherstone from Southwest Research Institute, and he's going to talk about low frequency dynamo waves resulting from modulated convection.
Great, thanks, Pashek. I'm putting a link in the chat for a movie I'll show later because it's choppy. You can open it now if you want, but anyway, so let me share. Okay. Does everybody see my screen?
Yeah.
Cool. All right. So yeah, so this is some work that I'm doing with Kinfe, who just spoke, also Kyle Augustin, Catherine Bloom, and Brad Hyman. So we've got kind of a mix of convection modelers and wavy people here. An alternative title for my talk might say, can we model active longitudes? And I'll try to stick to time here. We've already heard a little bit about active longitudes, but I'll just kind of recap. You know, these are regions of repeated flux emergence that are observed on the surface of the sun. They tend to persist for very extended periods of time. There's usually a handful present, often two. They have a really weak prograde rotation in the Carrington frame. So after you know, a solar cycle, they'll sort of have led the rotation of the rest of the sun by about 2.5 to 3 full rotations of their own. Yeah, they're very persistent with time. I don't have a lot of time to go into some of the background, but there have been some ideas on how these active longitudes, where flux continually emerges over time, come about. Malsumi, who I think is on here, has done a lot of work looking at the possibility of tachocline instabilities as a source of these regions of flux emergence. Some time ago, Maria Weber, along with Mark Misch and Yang Fan, put forth the idea that maybe where we have these preferred regions of flux emergence, they're actually somehow tracing the boundaries of large-scale convective cells deep down in the convection zone. And then there was another idea for a convective origin of active longitudes that I at least first heard discussed in Ben Brown's thesis work. And Ben and I were in the same research group in grad school with Yuri Tomre. And Ben, at the time, was doing a lot of convection modeling of so-called young suns. So he would really just take a solar-like convection model and then spin it up with a rotation period faster than the sun. So he would effectively create a lower Rossby number system than what people had been previously using to model the solar convection zone. And he found that there were certain regimes of convection that could arise, such as this one that I'm showing in the upper left here, where we've unwrapped the full sphere into an oval. And near the equator, you would get these really strong patches of convection, and then surrounded by these really weak patches of convection. And these strong patches themselves are also very long-lived. And he made this really suggestive plot in this 2008 paper where he stacked latitude or longitude strips with time. And you can see that there's this persistent structure in a rotating frame, and these also rotated a bit faster than the rotating frames, if I remember correctly. And so, you know, on the right for reference, I have another one of these magnetogram stack plots just to sort of show the similarity. And there was some discussion in this paper of, you know, is this potentially related to the active longitude phenomenon? But when he put magnetism into these particular models that he was running, and this is back when these sorts of things are actually really expensive, he came out with these magnetic wreaths that most of us have seen over the years, and these things can cycle but they're sort of axisymmetric in nature, and there wasn't anything that really looked like active longitudes. But there have been, quite a bit of time has passed, and so over really kind of the last 15 years, a lot of us have been running tons and tons of convection models and different Rossby number regimes. And Brad Hyman in particular did a really nice job, I think, a few years ago of sort of mapping out the parameter space that's accessible to these rotating systems. And he sort of drew out where we tend to see systems that have this kind of modulated convection. And so we thought we would look at the dynamo properties of those. And what we did is we took these models that Brad ran using the Rayleigh code. So these are inelastic. In his case, they were hydrodynamic models. We put MHD in them. These are spherical, they're three-dimensional, and they're fully nonlinear. And we just wanted to see, do we see any similar modulation in the magnetic field, like in these models? And I'll show you one example of one of Brad's models here, if it plays okay. And so a lot of the models that we've been looking at so far, and we've looked at a lot of these, but a lot of them are similar to this, and there's a reason for that. And you'll notice right off the bat, this is very laminar. We have some that are more turbulent. We have some that have convection at the poles. But what we really wanted to do was focus at first on models where the convection itself sort of has this property that it looks like there are interfering waves. And what we kind of expected to see was perhaps some sort of similar pattern in the magnetic field. So we put magnetism into these, and we often found strong magnetic structures at mid-latitudes, like people tend to find in low Rossby number systems where the convective overturning time is much less than the rotation period. And we would sample at the latitude where the magnetic field is particularly strong, and we would also make stack plots of our magnetic field. And then the question is, do we see anything similar to the observations, and that do we see low wave number magnetic structures that persist for very long periods of time, and which perhaps propagate in the rotating frame? Okay. And it turns out we found quite a number of these, but what's really interesting about them, I think, is that the wave number that we see is not really the wave number of the convection. So here I'm showing a stacked plot of the radial velocity on the left and the magnetic field on the right. These both share the same time axis. I've just labeled one in terms of rotation periods to give you a sense of how long we've run these for, and the other in terms of magnetic diffusion times across the domain. But the total extent and time is identical between these two plots. And so these convective structures, they do have somewhat long lifetimes, but they're still relatively short compared to what we're starting to see in some of the magnetic structures. And so here's just an example of a model where we see an m=2 modulation in the magnetic field, and it's got some very weak retrograde propagation that we can see there. If we were to turn the magnetic Prandtl number down in this case, so that we're half as diffusive, or twice as diffusive, excuse me, magnetically as we were, we move to an m=1 mode, and we see that this propagates more strongly retrograde. And in this case, we can actually see something in the velocity field, and I've shown the 5 velocity here. I should say at this point, I'm just kind of giving a quick overview of this work that's in progress. We're trying to write up a really small paper on this to have out kind of in the next month or so. So I won't get into too many details. I just want to show some examples. This is an interesting one. It's almost like we see sort of 2 different modes of magnetism kind of competing with each other. We've got an m=4 mode that's moving in the prograde direction, and that seems to be interfering with an m=3 mode in the magnetic field that's moving in the retrograde direction. And again, I just want to point out on the time axis over here how long these things live in terms of rotation periods, right? So a rotation period for a half solar cycle, 11 years, is going to be something like 120 20 rotation periods, and these things are persistent for considerably longer than that. Here's one. This is the one that had just a really clear signal. We got many, many cycles in this, and so this is one that we've actually started to really analyze as a group, kind of performing Fourier analysis of diagrams such as these. So this is an m equal 4 that propagates in the prograde direction.
Nick, 2 minutes.
Okay, that's not true. Just kidding. But I'll show just a quick movie. So here you can sort of see on the left the radial velocity that is associated with the convection that generates this m equal 4 mode. And you see the radial flow seems to be operating on a much more rapid time scale than the magnetic field. And the reason at the end of the day is that we've got a few convective waves in the system on the left, and it is the interaction of those with a few other modes in the magnetic field that are yielding this very, very low frequency modulation of the magnetic field. So if you were to watch the magnetic field near the surface or really at any depth and pick where it's blue, and over time it will slowly move towards this next reference line, and the reference line where it was at would be replaced by red. So I put a video of this in the chat, and you can have a look at it if you're interested. But in this particular movie that we're seeing here, 1 second is about 12, I think, rotation periods. So there's many, many rotation periods that are, you know, this movie spans many, many rotation periods. We started to map out the parameter space. Where do we see interfering waves, which I kind of call this irregular sporadic modulation and regular modulation. We seem to need to be at a pretty low Rossby number, where Rossby in this case you can think of, if you care about this sort of thing, is just Reynolds times Ekman. Take an RMS velocity and compute a Rossby number based on the system scale. And we need to be down pretty low, 10 to the -2 or so. But it's around there where a lot of the interesting Dynamo models, like that Petri showed earlier, actually sit, kind of in the between 10 to the -2 and 10 to the -1. So just in summary, I'll say, you know, we've found that there's actually a whole family of these Dynamo solutions that seem to exhibit some behavior that is at least similar in a sense to what we see with active longitudes. I didn't have time to go into kind of the Fourier and triad analysis that we've been doing, but for the system that I just showed, we're pretty sure that we can understand this in terms of the interaction of just 3 different convective waves, one of which we're pretty sure is a linear mode of the system. It's an m equal 3 mode, and then 2 nonlinear modes, which are 23 and 26 in M. And they all kind of look like thermal Rossby waves as far as we can tell. And then we've got some next steps, but really we just want to analyze this in a bit more detail, and I'll stop there. Thank you.
Thank you, Nick. Yeah, do you have questions? Yeah, Lauren, go ahead.
Thanks, Nick. That was really interesting. So I guess you kind of said it in the summary. I mean, does the time scale of the modulation, is it effectively the beat frequency between those thermal Rossby waves?
No, not quite. What we see is that we see magnetic field generated kind of in, so there's a lot of thermal Rossby waves in the system. They kind of come in clusters. So they'll range, for instance, from like m equal 20 to m equal 30 at one frequency, and then m equal 26 to m equal 30 something at a bit higher frequency. And what I think we're seeing is kind of an interaction between these convective modes and then some magnetism that is weakly generated by the other modes that aren't dominated. But it's not, I don't know if I would call it a beat frequency. I'd have to think about that. I want to be really careful, but you can't just take these convective modes and their frequencies and come out with the frequency of the m equal 4 mode. You have to have magnetic field generation by some neighboring modes as well. And we've sort of mapped that out, but I didn't want to show the confusogram here.
Okay. I guess, do you have any idea of what's causing that time scale?
I think it's very small differences in frequency between the magnetic modes that are prevalent on the smaller, on the high, at the higher M's, and the convective modes that are present at the, also at the higher M's. And why you get sort of these dominant interactions is unclear. Right now, we've just been mapping those out. Yeah.
Thank you.
Do we have any other questions? Okay. So next is a 15-minute break, and we'll reconvene at 1:55 Mountain Time.